Hey everyone, and welcome to this Forge College Explainer. So picking up right where we left off in our last lesson on translating token behaviors, today we're diving into performance and security considerations. We're going to give your Anchor token program a much-needed technical tune-up. You know, you've successfully ported your code from Solidity over to Rust. It compiles, it runs, and, well, nobody has hacked it yet. But as any seasoned developer knows, working is really only step one. Today, we're taking that functional code and transforming it into something lean, mean, and totally production-ready.
Here's the quick rundown for today's tune-up. We're going to look at EVM versus SVM realities, trimming cross-account rights, shrinking your storage, bulletproofing your authority, measuring upgrades, and finally, prepping for future upgrades.
All right, let's jump straight into Section 1, EVM habits versus SVM reality.
So when you transition from Ethereum to Solana, the underlying machine changes completely, right? And that means your mindset has to change with it. The architectural habits you brought over from Solidity, well, they might be quietly bankrupting you on Solana. Think of the EVM as this all-you-can-eat buffet. You pile your plate incredibly high, and the engine just sort of hides the state management away. But the Solana virtual machine, it acts way more like a strict a la carte menu. Every single byte you store pays daily rent in Sol, and every transaction has a super strict compute budget. If you treat Solana like Ethereum, you are absolutely going to hit your compute limits before your transaction even finishes its appetizers.
Moving right along to Section 2, trimming cross-account rights.
Our first real practical optimization is fixing fragmented account architectures. Why? Because touching too many mutable accounts burns through your compute budget incredibly fast. Instead of making multiple, super expensive cross-program invocations to individual allowance accounts, you need to consolidate. Basically, step 1, collapse your separate allowance accounts into a compact map right inside your token's main state. Step 2, pass a vector of user and amount pairs. And step 3, batch all those allowance updates in a single streamlined instruction.
The golden rule here is honestly so simple. Iterate locally, write once. By iterating through a vector of pairs locally in your program's memory, a single write to the token state becomes significantly cheaper. You pay the overhead of loading the account exactly once, process your batch, and save a massive amount of your compute budget.
Okay, Section 3, shrinking your storage footprint.
I want you to imagine every byte of data is renting space in a highly exclusive Manhattan high-rise. Seriously. A bloated data struct on Solana is basically living in the penthouse while you are footing the daily rent bill. We've got to downsize that apartment. You can drastically reduce your rent just by packing your structs. Try swapping out dynamic vectors for fixed-length arrays, compact your booleans into bit masks. Instead of using a whole byte for a simple true or false flag, just use a single bit and pack 8 flags into 1 byte. And finally, take that rarely used metadata, like string descriptions, and shove it into ephemera program-derived addresses so it stays completely off your hot path.
All right, on to Section 4, bulletproofing your authority patterns. Because look, running efficiently is completely useless if someone can just steal the car, right? Take a second to really let this terrifying thought sink in. You're transferring admin rights, you copy-paste an address, you miss one single character, hit enter, and poof, your entire protocol is sent to an unrecoverable black hole. It happens way more often in Web3 than people admit, usually followed by some very panicked Discord messages.
So, the industry-standard solution for this is the two-step authority handover. It's a brilliant security pattern that completely eliminates the typo risk. It requires an initiate step, where you set a pending authority with an expiration timer. Then there's a complete step, which requires the new authority to actually step forward, sign a transaction, and claim it. This proves beyond a doubt that the new admin actually has the keys before the old admin gives up control.
To fully bulletproof your protocol, follow this quick safety checklist. Replace any permissive, lazy signer checks with strict stored comparisons. If there's a mismatch, fail early. Just stop the transaction immediately to save compute. Add explicit custom error code so your front-end developers don't end up hating you. And most importantly, prove it works by writing exhaustive tests that actively try to hack your own permissive behaviors.
Next up, Section 5, measuring your code upgrades.
So, you've made these fantastic changes. But in software engineering, we don't just rely on good vibes, do we? We put the code on the dyno, and we measure it. To objectively prove your optimizations actually worked, follow a strict scientific method. Run your original baseline branch using anchor test and log the output. Then apply your new optimized feature branch. Rerun the tests, extract the exact compute units and instruction counts from those logs, and compare the deltas.
Your goal here is to fill out an acceptance criteria metric table exactly like this one, because the numbers don't lie. Showcasing a drop from 120,000 compute units down to 95,000, that's a massive 20% win. Fewer instructions mean less friction, and dropping your account size from 1,024 bytes down to 768 bytes literally saves you money on rent every single day.
The magic number you're really aiming for here is 10. A successful hot path optimization test should show at least a 10% compute reduction across the median of 5 test runs. Now, why 5? We use the median of 5 runs just to smooth out any little hiccups in the local test validator. Hit that 10% and you know for sure you've made a tangible impact.
And finally, Section 6, prepping for future upgrades.
These exact optimizations and security hardenings we've talked about, they serve as the absolute foundation for your token program's future lifecycle. Every single time you compact a layout, pack a struct, or change a permission model, you absolutely must document it in a design note. Explicitly track your layout compatibility, map out how your authorities migrate, and note any changes to PDA derivation seeds. If you skip this documentation, I guarantee your next program upgrade will almost certainly break your on-chain invariance and freeze your program.
Always remember this golden rule. Design your security hardenings with upgradeability in mind. Favor explicit two-step handovers and very clear permission records over opaque, quote-unquote, clever checks. Why? Well, because when you write migration scripts later, those tools need to easily and safely reconcile the state. Remember, overly clever code is basically the natural enemy of a safe migration.
Everything we've done today is really setting the stage. Your documented assumptions, your heavily compacted account layouts, and your objectively measured hot paths are the exact foundation you'll use in our next lesson on versioned upgrade strategies. You are now perfectly positioned to start treating your smart contracts like evolving software products.
And that concludes our technical tune-up, leaving you to ask yourself, is your code truly ready to migrate safely, or is it still held together by digital duct tape? I really hope after this the answer is a confident yes. Thank you so much for joining this Forge College Explainer. I strongly encourage you to visit forge.college to dive even deeper into this exact lesson and to explore a massive library of other fascinating Web3 topics. Thanks for hanging out, and I'll see you in the next one.